Okay, so since weak acids are acids that form an equilibrium with both the forward and the reverse reaction happening at a similar rate, what that means then is we can use our equilibrium approach to solve for concentrations of acids and bases, or for concentrations of weak acids and weak bases, and then as a result predict the pH accordingly. So just to give us an example to work with, let's imagine we have 1 gram of hydrofluoric acid, HF, which is a weak acid, dissolved in 250 milliliters of water. So the first thing we're going to do here is we're going to get the concentration of that HF in the water in the initial situation. So we have to get the moles of HF, which is going to be the mass divided by the molar mass, which is 1 gram divided by 1 gram per mole for the hydrogen plus 19 grams per mole for the fluorine. So 0.05 moles. And then I'm going to say I'm putting that in 250 milliliters of water. So my concentration is equal to my moles divided by my volume. Remember, these volumes always need to be in liters. And I have a 0.2 molar initial concentration for my HF. Okay, with that in mind, I'm going to write out my reaction. HF in the forward reaction is reacting with water as a proton donator. So in my initial situation, I'm assuming I have 0.2 molar HF. I'm not going to include my concentration of water because it's a liquid, which means it's fixed. So I'm not interested in it. And I'm going to assume none of it reacted, so I have 0 and 0 of this. My change will be a decrease in X, an increase in X, and an increase in X, and we're all 1 to 1 here, so we don't have to worry about any ratios. In my equilibrium situation, then, this concentration will be 0.2 minus X. This will be X, and this will be X. For a lot of these acid-base calculations, because these Ka's and Kb's tend to be very small, we can use the 100 rule. And if we can use the 100 rule, it's going to make our calculations a little easier. So let's check. To use the 100 rule, remember we have to do the concentration of the reactants divided by K, and it has to be greater than 100. So I have 0.2 molar divided by 6.6 times 10 to the negative 4, and that is equal to 303. 303 is bigger than 100, so that means we can do it. What that means then is our concentration here, 0.2 minus X, we're recognizing that X is going to be small. Remember, this is reactants over products, so here we're getting the products, and what we're saying is because it's very small, the amount of products being produced will be very small. So we can make the approximation that 0.2 minus X is going to be approximately equal to just 0.2. We'll check that at the end to make sure it was reasonable, but for now, that's going to make our math a little bit simpler when we do our K expression. For an acid, we call it a Ka expression instead of just a K expression, although it's just to name that as an acid. And here we're going to have the concentration, remember, only of our variable things. So the H3O concentration is variable, the F minus concentration is variable, and the HF concentration is variable, and we neglect the water because it's a liquid, which means it has a fixed density or fixed concentration. So we have X and 0.2 on the bottom, and this works out to 6.6 times 10 to the negative 4. So 6.6 divided by negative 4 times 0.2. So this is 1.32 times 10 to the negative 4. And this is X squared, and then I'll square root both sides. And I get X being equal to 0.0115. Now let's just check our assumption here. We said that 0.2 minus X should be approximately equal to 0.2. So 0.2 minus 0.0115 and I got 0.1885, which, I don't know, is that close enough for you? If it isn't, you could repeat the calculation starting with that, but since this is only for the sake of a calculation for a class, I think it's probably close enough, so I'm going to call that assumption okay. What that means then is that my concentration, if we go back, of H3O+, which is what I want for a pH, is equal to X, is equal to 0.0115. Okay? Now remember that our pH is equal to the negative log concentration of H3O+. So if I put that value in, I get 1.9. So for a strong acid, we can just take all of what's dissolved and assume it all makes hydronium and it all shifts to the right. For a weak acid, we have to do the equilibrium situation, but we can use the same equilibrium calculations we've been working on for the whole last week to predict a concentration, then take our concentration over and work with it to find pH.